Hey, pup. Hey, Rack.
Hello.
This video is about the math of Hadamard consistency. One could also say it describes the properties of Hadamard butterflies. We delve into the following properties. Hadamard domains identify exactly which values are valid within each node. The two different Hadamard domains are population nodes and non-population nodes. Population nodes allow values from 0 to 2 to the c, and non-population nodes allow values from minus 2 to the c minus 1 to positive 2 to the c minus 1, where c is the column number. Upper and lower nodes distinguish between whether values are added or subtracted. Partners are the other nodes within a box. And we delve into the fast Hadamard transforms of constraint vectors. Limitations of this video include that we only work with Sylvester transforms, the input vectors only have binary values, and the input vectors only have powers of 2 lengths. This is the classic Hadamard butterfly for the fast Hadamard transform of size 8. It shows which nodes are connected to which nodes throughout the computation, in other words, how nodes are grouped together into boxes. The solid lines mean add and the dashed lines mean subtract. The left column will be column 0 and the right column will be column 3. The top row is row 0, the bottom row is row 7. In general, columns will be numbered from 0 to log n, and rows will be numbered from 0 to n minus 1. All indices throughout this video will use a numbering related to this diagram. Hadamard domains. We require that the input to a fast Hadamard transform be a binary vector, which means that it only has values 0 and 1. So in column 0, the only valid values are 0 and 1. In other words, the Hadamard domain of all nodes in column 0 is 0 to 1. There are two different kinds of nodes in column 1. Half have Hadamard domains from 0 to 2, and the other half have Hadamard domains from minus 1 to 1. In column 2, a quarter of the nodes have Hadamard domains from 0 to 4, and 3/4 of the nodes have Hadamard domains from minus 2 to 2. In column 3, 1/8 of the nodes have a Hadamard domain from 0 to 8, and 7/8 of the nodes have Hadamard domains from minus 4 to 4. Note that the number of distinct values in every node in a column is always the same. It is 2 to the c plus 1, where c is the column number. Here we show how to compute the domain of nodes in column 1. Column 1 row 2 will be the sum of column 0 row 2 and column 0 row 3. The minimum sum will be 0 plus 0 equals 0, and the maximum sum will be 1 plus 1 equals 2. In column 1 row 3, we subtract the parent values. The minimum value will be the 0 of row 2 minus the 1 of row 3 to give minus 1. The maximum value will be the 1 from row 2 minus the 0 of row 3 to give 1. All other nodes in column 1 follow these two patterns. Here we show essentially the same pattern to go from column 1 row 0 and column 1 row 2 to column 2 row 0. The values in column 2 row 0 are the sums of the two parent nodes, and so they will range from 0 plus 0, which is 0, to 2 plus 2, which equals 4. The values in column 2 row 2 will be the difference. The 0 in row 0 minus the 2 in row 2 gives minus 2. And the 2 in row 0 minus the 0 in row 2 gives 2. Note that in this case, both parents range from 0 to 2. This is the other case. Column 2 row 5 adds the two parents. The minus 1 in row 5 plus the minus 1 in row 7 equals minus 2. The 1 in row 5 plus the 1 in row 7 equals 2. Column 2 row 7 is the difference of the two parents. The minimum value will be minus 1 minus a positive 1, which equals minus 2. And then the maximum value will be 1 minus a negative 1, which equals 2. Notice in this case, both parents range from minus 1 to positive 1. The Hadamard domains in these tables may seem to be a jumble. However, there is a structure. Sometimes the domain ranges from 0 to 2 to the c. We call these nodes population nodes because they count the number of ones in the input subvector. Sometimes the domain ranges from minus 2 to the c minus 1 to positive 2 to the c minus 1. We call these nodes non-population nodes because they count something else. Alas, we cannot explain what. Population nodes. This table is based on the Hadamard domain tables above. It indicates whether or not a node is a population node. In column 0, the value is true whenever the last 0 bits of the row ID do not contain a 1. In other words, always. In column 1, the value is true whenever the last 1 bits of the row ID do not contain a 1. In column 2, the value is true whenever the last 2 bits of the row ID do not contain a 1. This function computes whether or not a node is a population node. We compute the suffix mask by taking 2 to the column number and subtracting 1, which is the classic technique for generating a mask with the least significant n bits set. If we AND the parent row with the suffix mask and the result is 0, then this node is a population node. Otherwise not. These two functions compute the domain minimum and the domain maximum for a specific node. The minimum of the Hadamard domain of a given cell is either 0 or minus 2 to the column minus 1. The maximum of the Hadamard domain of a given node is 2 to the c or 2 to the c minus 1, where c is the column number. Proof that Hadamard domains have these ranges is straightforward. Base cases for columns 0 and 1 are given in the table above. The inductive step has 4 cases. When both parents are population nodes, then we are given that both parent domains range from 0 to 2 to the c. The upper child Hadamard is the sum of its two parents, so the upper child domain ranges from 0 plus 0 to 2 to the c plus 2 to the c, which equals 0 to 2 to the c plus 1, which is the population domain in the next column. Lower child Hadamards will difference the two parent Hadamards, so the lower child domain will range from 0 minus 2 to the c to 2 to the c minus 0, which equals minus 2 to the c to 2 to the c, which is the non-population range in the next column. When both parents are non-population nodes, then we are given that both parent domains range from minus 2 to the c minus 1 to positive 2 to the c minus 1. The upper child Hadamard will be the sum of the two parent Hadamards, so the upper child domain will range from minus 2 to the c minus 1 plus minus 2 to the c minus 1 all the way up to 2 to the c minus 1 plus 2 to the c minus 1, which equals minus 2 to the c to 2 to the c, which is the non-population range in the next column. And the lower child Hadamard will be the difference of the two parent Hadamards, so the lower child domain will range from minus 2 to the c minus 1 minus plus 2 to the c minus 1, all the way up to 2 to the c minus 1 minus a negative 2 to the c minus 1. This equals minus 2 to the c to positive 2 to the c, which is the non-population domain in the next column. This covers all 4 cases. Position properties include the following 4 functions. This table shows whether a node is an upper node or not, i.e. a lower node. Upper nodes return true, lower nodes return false. Note that column 0 alternates true, false, and so on. So isUpper is true in column 0 when bit 0 of the row ID equals 0. Note that column 1 alternates 2 trues, 2 falses, 2 trues, 2 falses, and so on. So column 1 is true whenever bit 1 of the row ID is 0. We note that column 2 alternates 4 trues, 4 falses, 4 trues, and 4 falses, and so on. So column 2 is true whenever bit 2 of the row ID is 0. This function computes whether a node is an upper node or not. The one left shift parent column effectively computes 2 to the n. The function returns true if the parent row ID ANDed with the mask equals 0. A related computation determines which node is the partner node in a box. This is useful for determining which nodes are the children or are the parents of any given node. When the parents are in column 0, The partner of row 0 is row 1, which differs by only having the bit 0 of the row ID flipped. Partner of row 1 is row 0, which also differs by having bit 0 of the row ID flipped. This pattern holds for all rows in column 0. When the parents are in column 1, the partner of row 0 is row 2, which differs by having bit 1 of the row ID flipped, and the partner of row 2 is row 0, which also differs by having bit 1 of the row ID flipped. This pattern holds for all rows in column 1. When the parents are in column 2, the partner of row 0 is row 4, which differs by having bit 2 of the row ID flipped. The partner of row 4 is row 0, which also differs by having bit 2 of the row ID flipped. This pattern holds for all rows in column 2. So here are 3 functions to compute partners. These functions are based on the parent columns and rows. The partner row is the row with the ith bit flipped, where I is the parent column. The upper partner row is computed by setting the ith bit to 0. The lower partner row is computed by setting the ith bit to 1. We're going to go back to the box pattern. We're going to compute values in various directions, and we're going to discuss the constraints of those values. The box pattern is shown in the diagram at the top. The parent nodes are M and N. The child nodes are O and P. The Hadamard transform is defined by taking the values for M and N and computing the values for O and P. However, it turns out we can compute those values in the other direction. If we take the equations that O equals M plus N and P equals M minus N, we can then solve for M and N in terms of O and P. The first step adds the equations for M and subtracts the equations for N. Then we simplify the equation, we divide through by 2, and then swap the sides, which results in M equals O plus P divided by 2 and N equals O minus P divided by 2. By rewriting these 4 equations, we can define any 2 members of the box in terms of the other 2 members of the box, as shown in the table. In our application, we are only concerned with taking M and N and computing O and P, or else taking O and P and computing M and N. This function computes the parent Hadamard value when given the position of the parent node and the upper and lower child Hadamard values. When the parent is an upper node, then we add the 2 child Hadamard values and divide by 2. When the parent is a lower node, then we subtract the 2 child Hadamard values and divide by 2. Alas, there are 2 problems with this function. The first problem concerns parity. In the upper box, if we go from left to right, if we're given M and N as, say, 2 and 1, when we compute O and P, we get 3 and 1. No problem. But when we go the other way, we have a problem. Suppose O and P are 2 and 1. Then when we compute O plus P divided by 2 and O minus P divided by 2, we get 1.5 and 0.5, which are not part of the Hadamard domain. We note here that if O equals M plus N and P equals M minus N, then O and P always have the same parity. For example, in the upper box, the parent values 1 and 2 have different parities, but the child values 3 and 1 have the same parity. So we must add a constraint that O and P have to have the same parity. If O and P do not have the same parity, then they may not be combined to calculate M and N. The second problem concerns range. When we go left to right, as in the top table, all values within the domain of M and N will actually compute values that are valid within the range of O and P. This is true for all of the box equations. However, when we go from right to left, not all combinations of values in the child domains will produce values that are valid in the parent domains. For example, if O ranges from 0 to 8 and P ranges from -4 to 4, then the equations for M and N can produce values from -2 to 6, even though they should only produce values from 0 to 4. Likewise, when both children are non-population nodes, when O and P both range from -4 to 4, the equations for M and N can produce values from -4 to 4, even though they should only produce values from -2 to 2. So this function takes a parent position and 2 children Hadamards and computes whether or not they would produce a valid parent Hadamard. First, it calls parent Hadamard to compute the Hadamard value that would be returned if it were valid, and then it returns a conjunction of two tests. The upper child Hadamard and the lower child Hadamard must have the same parity, and the new Hadamard value must be within the domain of the parent. Next, we will look at constraint vector properties. This is what we know about the fast Hadamard transform of Vi and the fast Hadamard transform of Vij. Vi is a constraint vector with only bit I set to 1, all others are set to 0. Vij is a constraint vector with bits I and j set to 1, all other bits are 0. In this case, I must differ from j. This matters because it limits the partial sums in the dynamic programming. Here's an example of Vi where I is 2. Notice that in V2, only bit 2 is set to 1 and all others are set to 0. So V2 will effectively select column 2 from the Sylvester matrix because all other values will be multiplied by zeros, and so the fast Hadamard transform of V2 will equal column 2 from the Sylvester matrix. So the properties of the fast Hadamard transform of any vector Vi are the same as the properties of the corresponding column of a Sylvester matrix. If I equals 0, then all of the output values will equal 1. Otherwise, half of the output values will equal 1, and the other half will equal minus 1. In either case, the minimum value is minus 1, and the maximum value is 1, and it must be one or the other. Here's an example of the fast Hadamard transform of V27. V27 is the vector with only bits 2 and 7 set to 1, as shown. This will effectively sum column 2 and column 7 from the Sylvester matrix. In row 0, 1 plus 1 equals 2. In row 1, 1 plus minus 1 equals 0. In row 2, minus 1 plus minus 1 equals minus 2, and so on. Because the columns of a Hadamard matrix are mutually orthogonal, we know that half of the cells in the columns must be the same, and the other half of the cells in the columns must be different. So, half of the values must sum to 0, and the other half must sum to either minus 2 or positive 2. The minimum value is minus 2, and the maximum value is 2.